Alright, so in this video, we're going to look at how to solve for specific heat in a calorimetry question. Calorimetry means that we are taking a substance that's hot and we're dropping it in a substance that's cold. And in calorimetry, we're assuming that all of the heat that is lost by the hot object is transferred to the colder object. And eventually, those two will reach a state of equilibrium where their final temperatures are the exact same. So in our question, it says a 25-gram sample of metal is heated to 225 degrees Celsius and placed into 500 grams of water at 20 degrees Celsius. If the final temperature of the water is 20.32 degrees Celsius, then what is the specific heat of the metal? So our equation for calorimetry, no matter what variable you're solving for, is always going to begin with negative Q, and this is going to be for the hot substance. Our hot substance was metal, because it said that metal was starting at 225 degrees Celsius. Q of the water, H2O. So now that we've established this equation, because remember, we know that whatever energy the metal is losing, it's being transferred directly to the water, because none of that heat is being lost to the surroundings. So now that we have established this relationship between the Q of the metal and the Q of the water, we can plug it in to the equation. The equation for Q is mc delta T. So we can say that negative m times c times delta T, all of this is for the metal, is equal to mc delta T for water. The only difference is we have to put the negative sign in front of Q because the metal is losing energy. It's an exothermic process. It's releasing the energy. So it'd be negative Q. Now, we can plug in all of our values. So for the metal, we know that the metal's mass is 25 grams. It says we're solving for the specific heat of metal, so let's keep that as C. And then the change in temperature. So the final temperature is going to be 20.32. So although it says that that is true for water, it's also going to be true for the metal because, again, these two things are being dropped into, or the metal is being dropped into the water. So eventually over time, no matter what, the water's final temperature is going to be the same as the final temperature of the metal. So we're going to subtract off the initial amount of heat. So 225 degrees Celsius is what our metal was initially at before it dropped into water. And we set that equal to the mass of water. The mass of water is 500 grams times the specific heat capacity of water. This is 4.184. The question didn't give it to us, but this is a pretty common one you would want to remember. And the final temperature of water, it says, is 20.32 degrees Celsius minus the initial temperature, 20 degrees Celsius. Now, we can go ahead and start to begin solving our equation. So I'm going to solve the left side. I'm going to go ahead and subtract 20.32 minus 225. And I'm just going to rewrite this. We're going to go real slow. So it's going to be negative 25 grams times specific heat capacity times negative 204.68 degrees Celsius equals. Now we can just combine all of these on the right side because all of these are like terms. There's no variable attached here. So we're just going to multiply straight through. So 500 times 4.184 times 0.32. So you should get 669.44, and our unit on this is going to be joules. The grams cancels out because that's in the denominator, and the degrees Celsius also cancels out. So this is our new equation, and on the left side we still have like terms. We have negative 25, and we're going to go ahead and multiply that by negative 204.68, and when you do that you're going to get 5,117, and the units are going to carry because you're multiplying grams and degrees Celsius, so we can't cancel any of that. Keep specific heat capacity as C and set it equal to 669.44 joules. Now all we have to do is divide both sides by 5,117 grams degrees Celsius on both sides of this. So we're going to do it again, 5,117 grams degrees Celsius, and you'll get a specific heat capacity of 669.44 divided by 5,117, and that gets us a heat capacity of 0.131 joules over grams degrees Celsius. That is our final answer.